Have you ever wondered what lies beyond the reach of our vision? We live in a world saturated with information, invisible to the naked eye. One such realm is the fascinating world of heat energy. Every object, from the icy expanse of a glacier to the roaring flames of a furnace, radiates this invisible energy. This energy, known as thermal energy, is the very essence of warmth and cold, constantly flowing and shaping our world in ways we often overlook. What if we could peer into this hidden world? What secrets would it reveal? Thermal imaging allows us to do just that, transforming the invisible glow of heat into tangible images. By understanding the language of heat, we can unlock a deeper understanding of the world around us. Thermal imaging cameras, with their ability to see heat, have revolutionized various fields from healthcare to manufacturing. One area where thermal imaging is making a significant impact is predictive maintenance. By detecting subtle temperature differences in machinery, technicians can identify potential problems before they escalate into costly downtime. However, interpreting these thermal images requires more than just pointing a camera at a machine. It demands a fundamental understanding of thermal science, the study of heat and its properties. Without this knowledge, the images remain a collection of colors, their true meaning lost in translation. Before we delve into the intricacies of thermal imaging, it's crucial to differentiate between two often confused concepts, heat and temperature. Although related, they are not the same. Temperature, measured in degrees Celsius or Fahrenheit, tells us how hot or cold an object is. It's a measure of the average kinetic energy of the molecules within an object. Heat, on the other hand, is the transfer of thermal energy between objects or systems at different temperatures. Imagine a hot cup of coffee cooling on a table. The coffee, initially at a higher temperature, transfers heat to the cooler surroundings until both reach thermal equilibrium. Measuring heat: joules, BTUs, and calories. To quantify heat, we use units of energy. These units help us understand and measure the amount of heat energy transferred in various processes. The most common unit in the International System of Units, or SI, is the joule. Joules are widely used in scientific and engineering contexts to measure energy. 1 joule is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. This unit is fundamental in thermodynamics and energy calculations. In other applications, you might encounter British thermal units or BTUs or calories. These units are often used in specific fields like heating, cooling, and nutrition. A BTU is the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit, commonly used in heating and cooling systems. This unit is particularly prevalent in the HVAC industry. A calorie, often used in nutrition, is the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. Calories are essential for understanding the energy content of food. Understanding these units is essential when evaluating the amount of heat energy involved in various processes, from industrial furnaces to the metabolism of food. By mastering these measurements, we can better control and optimize energy use in both industrial and everyday contexts. Section 5. Absolute versus relative temperature, Kelvin, Celsius, and Fahrenheit. Temperature scales provide a framework for measuring how hot or cold an object is. These scales are essential in various fields, from everyday life to advanced scientific research. We commonly use relative temperature scales like Celsius and Fahrenheit in our daily lives. These scales help us understand and communicate temperature in a practical way. Celsius, based on the freezing and boiling points of water, is widely used worldwide. It is particularly common in scientific and international contexts. Fahrenheit, another relative scale, is prevalent in the United States. This scale is often used in weather forecasts and household settings. However, for scientific purposes and many engineering applications, we use the absolute temperature scale, measured in Kelvin. This scale is crucial for precision and accuracy in experiments. The Kelvin scale starts at absolute zero, the theoretical point at which all molecular motion ceases. This makes it a fundamental scale in thermodynamics and physics. Unlike relative scales, the Kelvin scale directly relates to the thermal energy of a system. This direct relationship is vital for understanding and measuring extreme temperatures. Converting between Celsius and Fahrenheit can be done using simple formulas. These conversions are often necessary for various applications. Celsius to Fahrenheit, degrees Fahrenheit equals degrees Celsius times 9/5 plus 32. This formula helps in converting temperatures for practical use. Fahrenheit to Celsius degrees Celsius equals degrees Fahrenheit minus 32 times 5/9. Understanding these conversions is essential for accurate temperature measurement. Section 6. The power of thermal science in predictive maintenance. Understanding the fundamentals of thermal science is crucial for effectively using thermal imaging in predictive maintenance. This technology allows us to visualize heat patterns that are otherwise invisible to the naked eye, providing a unique perspective on the health of machinery and equipment. By analyzing the heat patterns revealed in thermal images, technicians can identify anomalies that might indicate underlying problems. These heat patterns can tell a story about the internal state of the equipment, revealing issues that might not be apparent through other diagnostic methods. These anomalies could be as subtle as a slight temperature difference in an electrical connection, which might suggest a loose or corroded connection that could lead to failure if not addressed. Or a hot spot on a bearing, indicating excessive friction that could result in mechanical breakdown, both potential precursors to equipment failure. Identifying these issues early allows for proactive maintenance, reducing the risk of unexpected breakdowns. For instance, a slightly warmer than usual motor bearing invisible to the naked eye could be an early warning sign of impending failure. This early detection is crucial in preventing more significant issues down the line. By detecting this early warning sign using thermal imaging, maintenance personnel can schedule timely repairs, preventing costly downtime and potential safety hazards. This not only saves money but also ensures the safety and reliability of the equipment. Thermal imaging, coupled with a solid understanding of thermal science, empowers us to see the unseen, to diagnose problems before they escalate, and to ensure the smooth operation of critical equipment. This technology is a game changer in the field of predictive maintenance. As technology advances, our ability to harness the power of heat will only continue to grow, ushering in a new era of preventative maintenance and industrial efficiency. The future of thermal science in predictive maintenance is bright, promising even greater innovations and improvements. Thank you for watching. If you like this video, don't forget to like, share, comment, and subscribe.